Out there in the vast, silent darkness of space, there are these objects with a power that's almost impossible to imagine. We're talking about the universe's ultimate titans, cosmic powerhouses that totally challenge our understanding of physics. So let's dive right in.
So what in the world do you call one of these cosmic behemoths? I mean, what kind of star has a strength so extreme it feels like it's bending the very rules of reality? Well, that's the big question we're tackling today.
And the answer is a magnetar. Now, in simple terms, it's a type of neutron star, but with a twist. Its defining feature, the thing that makes it so special, is an ultra-powerful magnetic field. A field so colossal it basically runs the whole show, dictating everything about the star's life.
Okay, to really get what we're talking about here, we need some perspective. It's one thing to hear a name, but it's another thing to understand the power. So let's try to wrap our heads around the sheer, mind-boggling scale of a magnetar's magnetic field.
All right, let's start with something we all know. The magnetic field right where you are, right now. That's Earth's magnetic field. It's only about half a Gauss, but it's what protects us from the solar wind. It's our starting point, our baseline.
Okay, now let's ramp things up a notch. Think about a hospital's MRI machine. That's one of the strongest magnets most of us will ever get close to. It comes in at around 10,000 Gauss. I mean, that's a huge leap from Earth's field, right? Well, you might want to hold on to your hat.
And here it is, a magnetar. We're talking about a magnetic field of up to a quadrillion Gauss. That's a 1 followed by 15 zeros. It's not just a leap, it's a completely different reality. Honestly, a number that big is almost meaningless by itself, so we need a better way to picture this.
So how about this for a mental image? A magnetar's magnetic field is so ridiculously powerful that it could wipe the data from every single credit card on Earth from halfway to the moon. Yeah, that's what we mean when we say impossible strength.
Okay, so the big question is, how does something this extreme even come into existence? Well, it turns out their origin story is every bit as dramatic as their power. Let's get into their violent life cycle.
So it all starts with a really massive star, way bigger than our sun. When that star runs out of fuel, it doesn't just fade away, it collapses and then explodes in a massive supernova. What's left behind is its super, super dense core, a neutron star. Now here's the key. If that brand new neutron star is spinning incredibly fast, this thing called a dynamo effect kicks into high gear. It's a process where all that spinning and churning motion creates and then massively amplifies a magnetic field up to these absolutely insane levels we've been talking about. And when I say super dense, I'm not kidding. Just to give you an idea, a single teaspoon of this neutron star stuff would weigh billions of tons, like the weight of an entire mountain packed into a teaspoon. That crazy level of compression is a huge part of what makes these things so powerful.
But here's the thing, that immense magnetic field isn't just sitting there peacefully. It's actively twisting and straining the magnetar's solid crust, putting it under unimaginable pressure. And eventually, something has to give. The crust just can't take it anymore, and it fractures. We're not talking about a little tremor here. This is a starquake, and the amount of energy it unleashes is just cataclysmic.
And this isn't just theory, by the way. We've actually seen this happen. Back in 2004, a magnetar 50,000 light-years away had one of these starquakes. The flare of energy that erupted from it was so powerful that in just 0.2 of a second, it released more energy than our sun will in 150,000 years. Think about that. It was so intense that even from that incredible distance, it actually hit Earth's upper atmosphere and measurably ionized it. It physically affected our planet from across the galaxy. So these things aren't just cosmic oddities to marvel at. They're actually crucial puzzle pieces for astronomers. For decades, scientists were seeing all these strange things out in the universe that they just couldn't explain. And as it turns out, magnetars might just be the smoking gun. Yeah, it turns out the whole magnetar idea neatly solves a bunch of these long-standing cosmic mysteries. You know those weird, repeating bursts of gamma rays scientists had been seeing for years? Well, that's probably the energy from starquakes. Those strange, anomalous X-ray pulsars, that's likely the heat coming off the decaying magnetic field. And maybe the most exciting discovery of all, those super brief, super powerful signals from deep space called fast radio bursts. In 2020, we finally traced one of them. And the source was, you guessed it, a magnetar right here in our own galaxy. What's so cool about this is that we could never, ever create these kinds of conditions here on Earth.
So magnetars are basically our only laboratories for studying physics at its absolute most extreme limit. The fundamental laws of nature actually start to behave differently in that kind of environment. So by watching them, we get to test the very boundaries of what we know about the universe. But for all their incredible power, these titans don't get to stick around forever. It's a classic story, really. Their existence is brilliant, it's violent, and it's surprisingly short, at least on a cosmic timescale. First off, they are incredibly rare. We've only confirmed about 30 of them in the whole Milky Way. And their active life, the time when they're actually having starquakes and flaring up, only lasts about 10,000 years. That is nothing, just a blink of an eye in astronomical terms. And ironically, the very thing that makes them so special, that insane magnetic field, is also what seals their fate. It eventually decays, and as it weakens, the magnetar just fades away. But not before its violent outbursts may have forged and scattered heavy elements like gold and uranium across the cosmos. And that rarity really is staggering when you think about it. For every 10 neutron stars that are born from a supernova, it's estimated that only about one has the perfect storm of conditions needed to become a magnetar. It needs just the right spin, just the right amount of churning inside. Everything has to be perfect. They are absolutely the exception, not the rule. And all of this kind of brings us to one last big idea. The fact that magnetars even exist proves something really important, that things we might think are impossible from our little corner of the universe are very, very real out there in the cosmos. It really makes you wonder, right? If these impossible magnets are real, what else is out there? What other cosmic wonders are waiting to be discovered, just waiting to completely redefine everything we think we know about the universe?